now theorem that we did, and then we'll take it from there. What's that? Yeah, we'll we'll do it eventually. Eventually, maybe at the last end of this class or maybe in the next class. We'll prove it. It's a very simple proof. We'll do it either in this class or at the end of this class or early next class. Uh, yeah, I mean, next class, I guess I should probably announce later. So next two classes are by Sarvesh, and then one class we are missing out. We'll reschedule on Saturday after that. ठीक है. Okay, chalo. So everybody with me on this thing, change of measure ideas. That's what Gaznav is all about. All right. So you have a random variable z, non-negative, strictly positive, expectation 1, that allows you to come with a new probability measure. The new probability measure has this property that when the original measure and the new measure gives positive probability to same sets, zero probability to same sets. So they are equivalent. In that case, one can define, this z is basically the radon-Nicotinamide derivative between probability measure p tilde and p, given by the following notation. Okay, and now since we have this property, by standard machinery, we also have this property. Right, we discussed that last time. All right, and now I can take my x to be y by z, right? I can do this since z is greater than 0. So then I get p tilde y by z is equal to EP of y. Or in other words, by taking y to be an indicator function, p of a is equal to EP tilde of indicator of a times 1 by z. So 1 by z is now the likelihood ratio. So 1 by z is dp by dp tilde. Okay, that's what we discussed last time. So it's just the ratio of dp tilde by dp. Okay, and all of this is kind of just nicely generalizing what you see in the discrete setting. Okay. Mhm. Mhm. Yeah, I mean, this is a generic result right now, right? Y- No, 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 no. I mean, see, you always worry that 1 by z need not exist or z need not exist. So here z was strictly positive, hence 1 by z existed. That's right. Yeah. Yeah. How do you define the? Yeah. That always works out. That's right. Yeah. Yeah. True. Now you can see it here as well, right? So if p omega is 0 and p tilde omega is not 0, then you run into trouble. Yeah. Mhm. Okay. Yeah. So let's carry on. Okay. So now we discussed that again with this z of t with the following properties, which allows us to change measures. We can define the conditional expectation z of small t, and the conditional expectation process is a martingale. That's a standard martingale that we've seen before, right? Then if q of a is given by having this variable z of big T through this representation, then EQ of y for any y which is f of small t measurable can have, it's equal to always EP of z of big T of y, but you can replace z of big T by z of small t, right? We should think of y and actually y is t. I mean, it's ft measurable. Yeah. Yeah, but f small t measure. Small t is fixed. Yeah. I mean, it's if you know you need not give it the notation y of small t. It just depends on all the. You think it's good for all t, then that gives you all t as ft measurable for all t. No, that may be so that will still be true that even if no, but y is just a random variable. So yeah, but so it is ft measurable for one t. Yeah. T minus one say. Uh-huh. Then I need another y. So then yeah, I can't make the statement for this y. True. So I mean, why is ft measurable? Intuitively, you can think about it as it's function of all the information till f of t. If f of t was just a sigma algebra corresponding to Brownian motion till time small t, then it's a function of Brownian motion till time small t. It's a path function. It's not a single variable function. It's allowed to be the function of the whole path. Okay, and the way we see this is, again, this expectation is equal to this expectation we argued. And then we condition on f of small t, right? We have this law of iterated conditioning. And now this becomes equal to, this quantity here becomes equal to, because I can take y outside when I do the conditioning. So then I'm left with this quantity right here. So this was easy. The more interesting part is when you look at conditional expectation under probability measure Q. So what's conditional expectation of y given f of s under Q? And again, you want to represent it under P, just so you know how you can move from one to the other, right? And that turns out to be EP of y zt given f of s upon z of s. So it's somewhat more intricate formula. ठीक है? So and why is that the case? You have to go back and see exactly what are we saying, yeah? I mean, that's just the right formula, right? I mean, I guess one nice thing is going to be that you'll see later, but we'll see that when we'll see it, I guess. Right now, I mean, that's the formula that works. Mm. So what we're really saying is that this guy here integrates like y under measure q on sets which are f sub s measurable. Right? That's what we mean when we say there's a conditional expectation. Right? So it integrates just y, right? Conditional expectation. Yeah, yeah. The left hand side, yeah, yeah. Yeah. This guy integrates like y, right? So hence, if I'm claiming this is equal to this, then this guy right hand side integrates like y. So I look at right hand side multiplied by I of a under q. I want to say uh, that this is integrating like y. ठीक है? So what do I do next? I first know that because this whole thing is fs measurable, right? I can go from q to p just by plugging in z of s here. I actually don't need this step, right? From q I go to p because q and p are related from as we discussed over here, right? We have this relationship. So EQY is EP by Z of t. When y was f of t measurable, if y is f of s measurable, then I could put Z of s here. So that's what I did here. I put Z of s here. ठीक है, under P. The random variable remains what it is. Now ZS gets cancelled, so I have this quantity right here. I can come back to Q by removing Z of t, by multiplying by 1 upon Z of t. And that's exactly what I need here. So it's not really a big deal in some sense, yeah. Hmm? Yeah, yeah, that's right. You could then talk about dividing by Z of x. Hmm.
What was Z again?
Z is
Like the one
this guy right here. It all started here, right? Z was our vehicle to go from P to Q. It's a reweighing function.
So when it's from P to P tilde, the Z that we got over there, so
Yeah.
the same thing over here as well.
Yeah, I mean, I guess just notation, but basically Z is a reweighing function. It's non-negative. Its expectations one. So it each looks at each and every omega, looks at P of omega of it, and multiplies by Z omega, reweighs it. So it gives you a new probability measure.
Even from P to P tilde, this is
If I call this Q to be P tilde, I've defined it right here. If I call it P tilde, if A, then we'll be doing P tilde. Oh, okay. Yeah, now you'll say it is not P tilde. P tilde. Okay. Okay, it's just a matter of P tilde A is given by this formula. So, yeah.
Also, just a correction, I didn't ask. So ZB should be greater than 0. Wow.
Yeah. That's right. Yeah. Yeah. Yeah, this should be greater than 0. Because you need that Z of small t also to be strictly positive always. So you can divide by it. Huh? Okay. So then we are. So far you with me on this? That we've got this conditional expectation formula. Sorry? In the second, this guy here.
you just take it expectation with respect to Q and then you show it's equal to
Yeah.
expectation with respect.
I mean, you've proposed to me that this is the variable, that's the conditional expectation. That's, you see, we are trying to come up, say that EQY given Fs is given by the following formula here.
We're trying to prove this.
We're trying to prove this, yeah. Okay. So we have to show that if we plug this in here, integrate with respect to measure Q on the set A in f of S, then it integrates like Y. Hmm? Okay. So we want to do this. Then we realize that, okay, from here to here, the jump is easy. I'm just going from one measure to the other. I'm just using the fact that Z of S takes me from Q to P, and 1 upon Z of S takes me from P to Q. ZS of brought me here. I got rid of this. And then I use iterated conditioning to rewrite this as EP by ZT I of A, right? It's EP of Y of Z of T given F of S. But that's equal to this quantity right here.
But shouldn't that be Z of S instead of Z of T?
No, the Z of S got cancelled already.
Okay. But you're conditioning on the measure F of X.
That's okay, whatever the random variable is. The random variable is YZT. So when I say, E of X given Y, that's equal to E of X.
Yeah.
It doesn't say, okay, X is what measurable or whatever. Those things are not an issue. Okay, so this point is relevant that we do go from here to here after cancelling Z of S. Now that we've come here, again we'll take ZT out and we go back to Q. So we are here then. And this is what we want to show.
Yeah.
Okay?
A is FS question.
Mm-hmm.
I is FS.
No, so from here to here, yeah, this one here, yeah. No, we use this property, right? Law of iterated conditioning. E of X given Y is a random variable function Y that has an expectation, same as expectation of X. Is a tower property, yeah.
You took the indicator inside and then took it out. And just
Oh, yeah, that's true. That's true, actually. Yeah, I should probably mention that as well, that first indicator, I could also take it inside, right? Because it's FS measurable. And then I apply the gradient condition.
Bro, shouldn't then the top part just be EQ of y given fs should equal to expectation over q and then this whole term itself.
Just say again, what are we meaning by top part?
So the red equation that we have, shouldn't that on the RHS shouldn't that be under E of q, the expectation of q over that term? Because in the end, we're just doing this thing.
So let me understand. You're saying this we have E of P here.
Yeah, and this whole thing under expectation over q.
This whole thing under expectation, the Q, okay?
Because see, when we try to start with the proof, we
Yeah.
have this whole thing under the expectation of q,
Right.
and then we derive just to the LHS part of the red equation.
Mhm. Yeah, no.
There's
So-
an expectation until Q in start with the proof.
What are you trying to prove?
नहीं, I'm saying ऊपर एक EQ आएगा क्या? The
नहीं
expectation.
नहीं 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 अगर Q,
Because in the end, you see, in the end, what we get is just the LHS of the top part.
yeah,
She's trying
yeah.
to show that the
No,
things that
but the point is if I put E of Q there, if I had here E of Q y z t given f of s upon g of s, this will not work. This will not be equal to this quantity. I mean, first of all, we've not really defined. I mean, this conditional expectation is what we are trying to decide, define. And we still haven't kind of figured out how to represent this. So we need this P here for everything to work.
Why not just like, so for this whole term, why not just like take an expectation of Q over this whole term? So like,
So then it's a, okay, so you that's kind of what's saying in your mind. Um, the point is, I mean, you don't want to find an expectation. Like conditional expectation is a random variable.
Mhm.
You'll then end up, if I just take expected value of Q of EP y z t given fs upon zs, I'll get some constant, right?
but then
Does anybody know what I'll get, by the way? Can you solve this for me?
But then this is not a constant, right?
Huh?
This is, we show that in the end it just like integrates like one into Q.
Yeah, that's right. So this will be a wrong answer, right? If I'm taking expectation of, so what's the expectation of this? If I take expectation of the right hand with respect to Q, then I'll get EQ of Y, right? So hopefully what I'm suggesting to you should also have that expectation. Can you see how that will happen?
no, it was showing me that's exactly what you showed.
No, but you can see from here also, right?
Maybe directly.
Yeah, you can go from Q to P by take.
P
No, but यहाँ से I can just write this is equal to EP of Y of ZT given F of S, right?
Yeah.
And now I can do the same thing again. Yeah,
exactly that is the longer steps.
that's right. Yeah. No, but I mean,
Then add it, then divide it, then cancel.
there I always had an indicator function. Now there's no indicator function here.
I mean, yeah,
That-
it's the same thing.
It's the same steps, of course. Yeah.
Isn't the entire
But the point is, yeah, you don't want the expectation here in definition of conditional expectation. So all you're some saying is that the expectation of this guy is equal to expectation of this guy, which is as it should be. If this is as a consistency measure. But the point is,
this will be true for all indicators, for all measurable steps.
right, in f of s, right. Um, so- yeah, so we need a candidate here, right? We need somebody which integrates like y, some random variable which is. So what do I need? I need a random variable which is fs measurable. Okay, and the candidate is this guy. This is fs measurable.
Yeah.
That you agree? So now it all has to do is it has to satisfy this property,
Which is-
which it does. Yeah. So this is the conditional expectation. Any other comments?
So basically, for any two change in measures can be constructed and
If they are equivalent, yeah. Because then if they're equivalent, then there's a radon Nicodemus derivative. So which serves as the random variable. It's uniquely you can do this.
This is very disadvantageous for it. We just use the fact that
No, no, we use the fact they're equivalent.
so
We
absolutely continuous with respect.
hmm?
So we constructed Q in such a way that it was absolutely continuous with respect.
No, but we wanted to divide by this thing, right? We wanted to divide by z of s.
We want to create.
Huh. Yeah. So it can't be, you can't divide by 0. Then we could have been in trouble.
Asking that to be strictly positive is the same as
Yeah, I mean, if I'm going from Q to P and P to Q, I need equivalence of measures. You know, because I can go one direction by absolute continuity, not the other direction.
so this is the same as asking that to be strictly positive.
Yeah, that's right. Yeah. Because again, the main thing is we are able to go in both directions. We had to go in both directions.
Interesting if Z is strictly positive, it's equivalent.
Hmm?
If Z is strictly positive.
ZT is strictly, yeah. Yeah, I mean, if Z of t is strictly positive, then Z of small t will also be strictly positive.
And then you're saying P and Q are equivalent.
Yeah, P and Q equivalent whenever Z of t is strictly positive.
Right.
Because, and why, what does that mean? That means that P of A equal greater than 0 if and only if Q of A greater than 0.
The same thing there on top as for P and P tilde, right?
Yeah. So P of A greater than 0 and Q of A equal to 0, and P of A equal to 0, Q of A equal to 0. So that's what equivalence means. ठीक. So any other questions? So let's carry on. This is still yesterday's lecture. Okay. Um, so then we defined this process here, right? Z of t, Z of small t now. Okay. And our claim is that this process is a martingale. And in particular, Z of big T, it's a mean one strictly positive martingale. So Z of big T can use as a change of measure to go from.
Just come to the zero, it's not.
Say again?
At times zero, it's not, and
That's right.
the martingale is also not.
That's right. Yeah. Okay, now in all of these, you need mild technical conditions on alpha S. And I'm saying this more for people seeing the video and saying, okay, you guys are just brushing over technicalities. So we are saying that we're brushing over technicalities. Okay. This is for posterity, huh?
What is some condition?
Well, what are some conditions? Meaning all the integrals we see should be well defined. But otherwise, let's not go into that. There's a Nozica.
Yeah, I want it to be finite. It will have to square to be able to work.
Yeah, all of these should be there. So there's some nice sufficient conditions which achieve this. Novikov condition, if I remember correctly, maybe you can search and tell me, but it's going to be this, I think. This would be sufficient for defining all this. But certainly alpha S being bounded would work. All right. Okay, now it was that. Oh, cool. All right. So now, how do we proceed to analyze to show that it's a martingale? We realize it's an exponential of an Ito process. Exponential of a Ito process is a function of Ito process. We know its identity. So we write the exponent as x of t. That's an Ito's process. This becomes a shorter notation for it, right? So far with me. Now we apply Ito formula to z of t. Z of t is just e to power x of t. So z of t dxt, and then 1 by 2 z of t dxt dxt.
Okay.
Okay. So we're looking at z of t is equal to e to power xt. So it's a function of x of t, right? So when we apply Ito's lemma, it's f prime xt dxt, and then f double prime xt by 2 into dxt dxt square. Dxt dot dxt, yeah, right here. Okay. Then we simplify this thing here, and this term was designed to cancel. So what you're left with is negative of alpha dzt dvt, which is a stochastic integral. So z of t is a martingale. Okay.
Can you also clarify why the stochastic integral necessarily has so can you guide explicitly the expectation once? Because I'm not seeing why conditional expectation of ZT given FS would be ZS. or it's just this formula?
I mean, stochastic integral is a martingale we proved already, right?
Okay, okay.
You know, we showed you that this integral was a martingale, and intuitively, again, integral think of it as kind of limit of simple processes. For simple processes, we saw how I was a martingale. It's just random variable increment plus random variable increment. So, sum of all those things.
I mean, now we saw the similar ways that right? We saw that this guy Gaussian.
No, this is alpha s need not be deterministic. Deterministic. It's a Gaussian only when alpha s process is a deterministic process. Plus, we have alpha s times z of s. Yeah. No, it's important to be clear on these things. Yeah.
Z0 was defined as one. Is it? No, you defined it over here.
Maybe we define z of t for all t as follows. It's a process here. So when you put t equal to 0, you get exponent is 0, so you get 1. Okay? All right. So we get the following quantity. We'll come back to this quantity. I will need this a little bit later. Basically, the likelihood ratio that we defined is a likelihood ratio process in this case. That's a martingale. See, typically, if I told you, okay, what do I want to say? Let's say x omega is equal to dp. P omega by P tilde omega. Let's keep everything discrete, right? Then expected value of x under P tilde is summation. Yeah. P omega by P tilde omega into P omega into P tilde omega. And that's equal to 1. So then the random variable is equal to 1. But now we are defining a whole process. So it's a process which is a martingale with mean equal to 1. Okay, so that's the extra thing we're getting. All right. Okay, so now we are moving towards today's lecture. So for Levy's theorem, we had this probability space and a continuous martingale M of t defined on this space. So M of t is a process, it's Ft measurable, it satisfies the martingale property, M of 0 is equal to 0, just like in Brownian motion. It is continuous martingale in the sense M of t has continuous paths, omega by omega. So the theorem is that if its quadratic variation is dt, just by looking at its quadratic variation, you can conclude it's a Brownian motion. Okay. So it's a big theorem, we're not proving it. It requires some effort to prove this, but it's very useful. So that I want you to take on faith. Right? Okay, now let's see a consequence of this, an example where it's useful. Now suppose I have two Brownian motions, B1t and B2t, which are independent of each other. And now I construct another process B of t, which is a combination of these two. Right? It's not a convex combination. Because rho plus square root of 1 minus rho square is not equal to 1. Yeah. Rho square plus 1 minus rho square is equal to 1. So I got this combination. And my claim now is that this combination, this combined process, is again a standard Brownian motion. Right? One way can be that you note that B1t at time t is Gaussian, B2t is Gaussian, sum of two Gaussians is again Gaussian, match the mean and variance, so you get a Gaussian process. Then you also argue that increments are independent.
Big as T, you need to show covariance.
They will be the same, the t is fixed for same t. That covariance issue comes up if I go from t to s. You're right. I mean, now.
So that was the Gaussian process continuous. Now it's Brownian motion.
Okay, so your point is we have to show bt plus s minus vt is independent of b of t, right?
That.
Hmm.
So we have to show 4 properties for a Gaussian process to be.
Yeah.
Brownian. 4 properties. Covariance of BT and BS is min of S.
Sure, which is okay, yeah, which is same as saying BT minus BS is independent of BS. Yeah, I mean, it boils down to the same thing. Yeah. Because that's how you show that the covariance is S, right? Dekho, how do we show that BT, BS, let's just take S is less than T. We want to show this is equal to S. That's what your point is, right? And we show this by showing that it's E of BT minus BS plus BS into BS. We write this in following manner. BT minus BS is independent of BS, so that becomes 0. And then E of BS square is equal to S. So it needs to be shown. But effectively, it's relying on showing that the independent increments are independent. All right. Right. So you could do all of that here. But now you have an easier way of doing it, right? So what's the easier way? Yeah, Levy's theorem. Yes, it's Paul Levy. Nothing to do with the genes, yeah. It's Paul Levy's theorem. Paul Levy, I mean, you can go to Rama Kant's page. Rama Kant was a professor who came here. He's works in math finance. But he has this whole page he maintains on Paul Levy, the story of Paul Levy and all that. It's because it's a fascinating story. Yeah, I had mentioned this earlier, right? Even after mentioning it, I've not gone through the page myself. But I mean, but I know that Paul Levy has a very interesting story, so it's worth kind of going through. He came up with great probabilistic insights, but was generally not well regarded in the French math school. So that's kind of the gist of the story.
Right, it was all coach numbers that.
Hmm?
It was all coach numbers that he gave.
Yeah, something like that, maybe later in his life.
Like too old by then, right?
Some,
These things came much.
yeah, you should read it and tell me. I'll try to make time to read it too. But yeah, that's correct. Okay, so now we're on camera. I need to be more careful. Okay, so what do we need to do? We know B0 is 0. We know BT is continuous, we know, right? Because B1t and B2t are continuous functions. So BT is also a continuous function, omega by omega. That we do know. Why is it a martingale?
Linear combinatorial. I mean,
Two martingales, yeah. Yeah, that's it. So it's a martingale. So all you really need to show now is that the quadratic variation of BT is equal to T. So then you just do dBT times dBT, right? Okay, so I've not shown you so far that B1t, dB1t dot dB2t is equal to 0. You know that.
but the independent Brownian motion.
Yeah, but we haven't shown that yet, right? Yeah, I didn't realize that. So we'll show that in the next slide. So because that's the case, so you get dB1t, dB1t, you get rho square from there. Hmm? I'll just show in the next slide. Yeah. Yeah, I should have had it earlier. But if you accept that, then it's clear, right? 1 minus rho square, so it becomes 8. So that everything works out.
Square D quadratic. Quadratic relation defined.
No, that's what we mean by quadratic. dBt dot dBt. That's quadratic variation. We always, when we write dxt dot dxt, we meant quadratic variation of xt. And the way we define, of course, is, huh? We do not mean multiplication. It's just the Box rules that work out. But basically, we mean we take the xt process, partition the interval, look at the quadratic deviation, sum them up, take their limit in the L2 sense. That's quadratic variation. And that we denote heuristically as dxt dot txt. And we apply box calculus and we get the right result.
Any variation which is less than quadratic,
Huh.
finite, and any like n variation which is greater than quadratic would be zero.
Yeah, Yeah, so that's the whole intuition that for you're saying for a function of Brownian motion, quadratic variation is finite, any less variation is infinite, any more is zero. It's not really relevant here, right? I mean, those are true facts, but not relevant to this discussion right now. That will be, yeah. Mhm.
Sorry.
Yeah, yeah.
So is there any book which has explicitly the mapping from a like sort of formal uh, mathematical terms and this DBT notation? Because it seems that dxt originated in the sense of like stochastic differential equations, and it's not clear to me why let's say dxt into dxt should represent the quadratic variation. I mean, I get that it's a heuristic sort of shorthand, but is there a place where you can look into
Uh,
the shorthand?
well, I mean, you have those references I gave in the sheet,
That
right?
they'll get the
No, I would, Michael Steele is okay. If you want to see something more technically detailed, then Kratzas and Shear. Okay. But yeah, so we showed you box calculus. The point was to talk about quadratic variations there. So where am I? I'm here. Right. I mean, the point is going to be you're going to look at this quantity, right? xti plus 1 minus xti the whole square. Right? Now, xti plus 1 minus xti, you'll have a Taylor's expansion. So you'll get your bti plus 1 minus bti square into the corresponding term in the integral. And then you'll get some ti plus 1 minus ti the whole square. In the ti plus 1 minus ti, you're doing the whole square terms. Cross terms you'll be able to show are 0. The square term involving ti plus 1 minus ti, the quadratic variation contribution from there, that will be 0. The only thing you'll be left with is contribution from, I mean, you have to see all this, but bti plus 1 minus bti, there'll be some integral here, alpha ti, right? So now, so I guess let me just see if I can go to a separate page. What I'm trying to show is that suppose my dxt is equal to alpha t dbt plus say beta t dt. Okay. So then roughly speaking, I have xti plus 1 minus xti is alpha ti into bti plus 1 minus bti plus beta ti into ti plus 1 minus ti. When I square this term right here, when I square it, I get a square term here, I get a square term here, and I get a cross term. Okay? This term squared will vanish, the cross term will vanish. What I'll be left with is alpha ti bt. We argued earlier, right? That remember we argued that the cross variation of these guys is 0 because bt is a continuous function, so you can come and bring it outside. Dt square is 0. Yeah. Yeah, so this guy, our argument is saying that okay, dt dot dt is 0 and dt dot dbt is 0. So what you're left with is dbt dot dbt, but into this alpha ti square. When I square this, I get this alpha. So it's kind of clear how the argument would work, right? And when you see it, it's no big deal. It's exactly just. So yeah, alpha ti square. Because I'm going to square the whole thing, right? I'm going to square this guy, then I'll get this term here into dt. Yeah. Okay, it's kind of intuitively kind of clear what's going on, right? Because I'll just again, well, whatever. Let's move on. We can take it for granted, but it's very clear why it works. It's just, yeah.
The book has a good explanation for it as well.
Yeah, which book?
No, sorry, this was
Yeah, ChatGPT is good actually.
Because I was asking, I was looking for my Steam for this.
Mm-hmm.
I Google said, the big thing is GPT square is that's alpha square.
Yeah. So now to your point about, okay, how did we show, yeah, how did we show
The cross term is zero.
the cross term is zero? So I'll just give a heuristic argument for that too. I mean, how do we basically assume that d b1t dot b2t is equal to 0, right? Because we also assume that. And that is kind of, again, the cross variation has the following form, right? And these are independent variables. So these are just t by, I'm again assuming that the gap now is equidistant. So it's t by n into summation I equal to 1 to n ui vi, where ui and vi are zero mean variables. Right? Each of these guys here is just t by n into normal 0, 1. Okay, I guess in this case it's small t, the way I've written it. Yeah, small t, sorry. No, well, yeah, I mean, this is all, I mean, I've telescoped here, right? This is telescope some here. No, it's, well, in the sense, I mean, I've chopped up the line and kind of given you smaller terms. But yeah, it's not like it's canceling or anything. That's not happening. So what I want you to kind of think about here is, because we are seeing more than how it's going to see. We're saying this guy is basically, it's Brownian motion, right? Between this interval it by n and I plus 1t by n. So it looks like normal 0, 1 into square root of t by n, square root of small t, I guess, in this case. That right? It's a distribution of this increment. Nothing surprising here. This guy is also square root of t by n into normal 0, 1. Both these normals are independent of each other. They are not dependent. That's important. And that's true for for every I, this is true. So what this guy looks like in distribution is t by n into summation ui vi, ui times vi. ui and vi are both mean 0 independent variables. So the product is also mean 0. Okay? Independence what we are using. If they were dependent, then the mean 0 property will go away. Right? And variance is not a big deal. It's independent, so you know what the variance is going to be. It's all finite. So those are not.
Strong law.
Hmm? Then by strong law of large numbers, I know that this quantity right here is converging to 0. It converges the mean of ui vi, right? So that's 0. And just t is just fixed. Well, this is small t, but it's just fixed here. So the cost variation is going to 0. Okay? Yeah. Why does this term represent cross variation?
Oh,
I mean, huh?
I mean, in some over each period, so you chopped up your entire timeline into. So you understood D, but thought D is.
Yeah, no, you asked me to go for a much longer detour, but the point is this. Suppose I'm trying to show, let's say, I'm trying to find quadratic variation of alpha times b1t plus beta times b2t. What will I do? I'll chop up the interval from 0 to t into small partition. I look at the square deviations. So I look at terms of the form alpha b1 ti plus 1 plus beta b2 ti plus 1 minus alpha b1 ti minus beta b2 ti. I look at these kind of terms and I'll square them and I'll sum them up. Okay. Now when I'm doing this, I'll have this cross terms. When I open up the square, I'll get the cross terms, right? So my argument here is that the cross terms will vanish, right? I mean, I'll get these terms when I square this, I get alpha square times b1 ti plus 1 minus alpha square times b1 ti. Alpha times b1 ti plus 1 minus alpha times b1 ti, the whole square. And that will converge to alpha square into t. That's just... Hmm? Alpha square? Chalo, yeah. No, no, you're fine. I just don't want to spend that much of time on this, but let me just do this quickly. No, let's just do this. अब बात यहाँ तक आ गई है तो b1 ti plus 1 minus any plus beta b2 ti plus 1 minus alpha b1 ti minus beta b1 ti, the whole square, I equal to 1 to n. That's the kind of stuff we're looking at, right? So now I'll take these two together. So I'll get summation alpha square comes outside b1 ti plus 1 minus b1 ti, the whole square. And this will converge to alpha square into t.
Yeah.
And similarly, I'll have beta square into summation b2. That's right. So this will go to, again, beta square into t. And the cross term, that will go to 0. Because alpha and beta are just well behaved. So, they're not going to make things blow up. Okay, so that's a big idea. Okay. And you always have ChatGPT to fill you in on details. Yeah? To the statement of Levy's theorem. All the way to Levy's theorem. Yeah.
So I that not in the market.
I mean, I can always... I mean, I can always construct a Brownian motion kind of object which on rationals takes values 45. So it's discontinuous, and the quadratic equation will be unchanged. I mean, I need to specifically construct a continuous process. Yeah. So in some sense, all the properties that are satisfied by continuous Brownian motion are also satisfied by this Brownian motion, which is discontinuous on the rationals. All the other properties. So I need to explicitly state that I have continuous paths, and I have to look for that version. So it's, we're just kind of imposing the fact that we have a continuous martingale M of t. All right. So we've got this now, right? We understand this part. Okay, so now we understand Levy's theorem. Okay, where are we? Yeah, so we understand Levy's theorem. All right. So let's talk about Grasnov's theorem. We were here, we discussed this last time as well. See, now we're going to use this guy to change the probability measure, right? And the Grasnov's theorem is saying that if you reweigh, if you have a probability space, you have a Brownian motion, and you reweigh the paths using this z of small t, this process, so z of big T up till time t, if you reweigh in that manner, then your you get a new probability measure, right? So I don't know, the notation I'm using is p tilde. You get a new probability measure as follows.
Okay.
Okay, we got a new probability measure by reweighing the paths. Okay. Under that probability measure, this guy will be standard Brownian motion, b tilde t. Meaning your bt will now be b tilde t minus 0 to t alpha SDS. It will have distribution of b tilde d minus this drift term here. So that's what Gauss's theorem is telling you. Under p tilde, b tilde t is a standard Brownian motion here. Okay, so just to understand this better, take your alpha s to be a constant alpha. Then when you reweigh, and I guess maybe think of this as big T, but when you reweigh, the bigger values of Brownian motion are getting smaller weight. So you're multiplying them with minus alpha into b of t. Okay? Alpha is positive. Negative values are getting larger weight. So what you've effectively done on the new probability measure, so you ask yourself, well, what does this new probability measure look like once I've done all this? Under a new probability measure, b tilde t is Brownian motion, but your original Brownian motion now has a drift minus alpha here. Yeah. So this reweighing, that's what is achieved. Is this clear? But basically now you've got a recipe to go from one probability measure to another. Under when you have Brownian probability space using these likelihood ratios. Yeah.
So if I have some P and some P tilde,
Yeah.
does there always exist an alpha S process which would
Relate them in this manner, yeah. Under conditions, if your underlying sigma algebra is only generated by a Brownian motion, then this is true. We'll argue this using martingale representation theorem.
wait, so the underlying algebra is only generated by me.
Yeah.
Then we can't.
Then we can.
Otherwise we can't.
Otherwise, you could construct examples where this may not be true. Because your f of t then can have more sources of noise. Right?
But then you always
So then you can have two probability measures which are not related in this form.
okay.
There may be other noise that's also coming up.
So in that time, what we say, okay, let's say you're in a sigma algebra only has this only generated value of Brownian.
That's right.
Then for all sigma is under these mind bounded conditions, so it will work out.
That's right.
For other sigma algebra, it may work out, but not in the same general.
That's right. Yeah. That's true. That's absolutely correct. I mean, those cases I can add all kinds of extra noise in my f of t, right? So the two probability measures need not be related to this through this likelihood ratio. They may be related to other sources of noise as well. Right? This is all the noise here is coming just through the Brownian motion. So I mean, you can kind of get a sense of what that might mean, but we don't want to go there right now. Okay, so proof relies on showing that that b tilde t is a martingale, right? What have we done? We've just kind of defined this new process, right? Which we know is not a martingale under P. Because BT is a martingale, this will not be a martingale under P. We'll show that's a martingale under P tilde. Okay, is this clear?
One simple question.
Uh-huh.
Suppose I had a process X,
Mhm.
which equals to some X tilde
Mhm.
plus some stochastic integral.
Mhm.
And I say that X tilde is a martingale.
Mhm.
Then X tilde plus some stochastic integral would also be
That's
martingale.
right. That's right. Yeah.
But here, since it's a drift term, it won't be.
That's right. Yeah. Yeah. Yeah, I mean, this is exactly not a martingale, right?
So it is a martingale under
Hmm.
P. So you fix it.
Huh?
It is a martingale.
B of T is.
B of tilde and B tilde.
Is not.
So this is a martingale under P. This is not a martingale under P.
Under P.
It's not a martingale, right? It's just a drift term. Yeah. Drift term is not a martingale. It's a deterministic evaluate. Unless it's a constant, it's not a martingale.
Okay.
Okay. All right. So this is what we are going to show. We are now playing with this guy here. So Grishna's theorem is all about playing with this new sequence of random variables and showing that this new sequence of random variables is a Brownian motion. And the way we show that is we show it to be a martingale. We under P tilde. It's not a martingale under P for sure. Under P tilde, we show it's a martingale. We also observe that it's a continuous process at time t. Okay. And we also observe that. So what else do I need to make this a Brownian motion? If I'm telling you it's a Brownian motion, I need to show you that B tilde 0 is equal to 0. So we need the quadratic variation of dt. And why is that the case? Hmm? No, quadratic variation is not. No, quadratic variation is the fact if the quadratic variation is dt, then it's a Brownian motion. That we'll use Levy's theorem. That the fact that the quadratic variation is dt is not from Levy's theorem.
Can we just, I thought you said, how does that tell us that is?
Yeah. So why is the quadratic variation equal to dt?
Because your dvt dt term will be 0 by box calculus. Then
Yeah.
just be like a dvt square which will.
That's right. So when I square this guy, dbt dot dbt is equal to dt. Yeah.
So what exactly do we mean when we say for the quadratic variation to be d? Because dt is a fixed guy, but quadratic variation is function of omega. So I was saying for all omega with probability 1 this should be d.
That's right. Yeah.
So then your measure never really mattered because the equivalent measures measure you said you measure.
Yeah.
So dvt square equals to dt, the main dvt square is. I mean that the reason we could do what Google
Yeah.
said is because measure 0 sets but also measure 0 sets. So if dp2 square is dt probability 1, then d tilde square equals to d2 probability 2.
Yeah.
Right?
I mean, that's true. At the end, we are going to just look at this process and find its quadratic variation. Right? We know what the definition is. In that definition, these guys will not matter. And dbt dot dbt was equal to t almost surely. Yeah.
Because that
And
equivalent
no, you make a very nice point that quadratic variation is an almost sure result. So it's true under all equivalent measures. Huh? So that's true.
reference should be almost 1.
Yeah. It should be on a set of probability 1, which is almost surely. I mean, there were nuances, but yeah, this kind of captures the fact that since it's almost sure, we don't worry about the fact that it's under measure P tilde or P. Okay, so it is continuous in T by definition. dP tilde T, dB tilde T is equal to dt from the quadratic variation consideration. So all we need to show is that this is a martingale under the new measure. How do we show this? We show it later. Okay. Okay, how are we doing on time? Okay, we might still be able to do it. So let me show that to you right now and come back to this example. Maybe that's better. Yeah, we can do all of this later, I guess. Maybe I don't need all this. No, but I do need Ito's calculus, multivariate Ito's calculus. So I can't do this right now. So let's just do this part again, the Gaussian example again. So consider B1, B2 to BT now no longer a Brownian motion, but such that the B1 x1 is n01 and the increments xm bm minus bm minus 1 are also n01 independent of b1 through bm minus 1. Yeah. One is the So let me understand your question. We have two Brownian motions, and translate in the sense, okay, you say two basically Ito's processes, B B tilde T is equal to BT minus say alpha S ds 0 to T. You mean like this? Huh. And we assume that BT is Brownian motion. How do we show B tilde T is Brownian motion?
What's the right of construction?
Hmm.
Or how do you know
I mean, right now we constructed it as follows, right? This we could do.
this like just generally speaking?
What's the rationale for constructing B tilde T? I, I see, I see. Uh, but you agree that BT is a well-defined random variable. B tilde T is a well-defined random variable. We want to come up with a change of measure under which uh, B tilde T is Brownian motion. And you're asking me how do we do that? By Garzov's theorem. The Garzov's theorem tells you that if I now use this guy, because I know this alpha S process, right? So if I take this Z of T as follows, and I construct a new measure as follows, that under this new measure, this B tilde T is going to be a Brownian motion.
So,
Huh.
just don't want to be confused. I just realized that. Is that capital T or is that a stopping time tau? Because
Is there a stopping tau showing up somewhere?
you got the definition. What line was
Oh yeah, no, it's a typo. It's
stopping tau is that?
you don't want to go there right now. You don't want to confound the confusion. No, this is just I think when the handwritten notes were converted to LaTeX, this T became tau sometimes. ठीक है. But is this guy? So this is important. This is the main thing that you can construct B tilde T in this kind of funny way, and then you can construct a probability measure under which this B tilde T becomes a Brownian motion. So you can really construct any process in this way can become a Brownian motion under a suitable probability measure. And that gives you a lot of tractability then, right? That allows you to, do fair amount of analysis and draw conclusions. So we'll do that.
So probability measure.
Hmm.
Alpha is which would yeah.
Probability measure is a reweighing probabilities, right? And under those probabilities, this guy's distribution is changing now because of alphas. Yeah, it's changing now in just the right way. So you've changed it in just the right way. So now it becomes, so for example, suppose alpha s is constant. So earlier this was bt minus alpha times t. So this was a Brownian motion which had a negative drift. Okay. But now I've reweighed the probabilities. So I've given kind of more probability to how I've done this in here. Uh, yeah, no, just give me 1 second. I want to say that for B tilde T, I reweighed the probabilities in such a manner that I've given higher values to larger values of B tilde T, lower probability to lower values of B tilde T, so that now my B tilde T becomes, but actually what I want to say for all of this to work, that's why I'm looking so confused. This should be plus here. So originally under my original measure, BT is standard Brownian motion, B tilde T, the way I've defined it, has positive drift. And now I've reweighed probabilities in such a manner that large values of BOT have gotten smaller weight, small values of BOT, negative values of BOT have got larger weight. So now this guy which had positive drift then ends up becoming standard Brownian motion under the new probability measure. So is this kind of clear? So it's not such a trivial fact. So it takes a while to kind of see all the pieces that are moving around. Okay. Main thing is random variables distribution changes under a change of measure. Yeah, it has a different distribution now. All right. So now let's look at this example. just to homing this point that this should not be so surprising, all that's going on. Yeah, Bharat. So x1 through xm are just normal 0, 1, right? So P of x belonging to set A is just, and these are independent, so it's just the product of the probabilities, f of x1 to f of xt, x1, all x belonging to set A. Okay, that's basic probability.
Wait, Prof, is there like a typo between small x and big X?
No, this is small x is, no, it's fine so far. The small x is coming here.
Okay, the
Small is just a point here.
Okay.
Yeah. Okay. So I'm just summing up all the points which lie in A, and on those points I'm summing up the probabilities. Now if I take m of t as follows. Summation mu I xi minus summation mu I square. Now this m of t I can use to change the measure of these, and this random variables is now a different distribution. Okay. First of all, you should also check that this m of t has is strictly positive, that's clear, but that has mean 1. Can you see that? Yeah. In this case, yes, of course, yeah. Ah,
Guys, when you say capital X is on order of XT,
hmm yeah,
we just simply the N01 independent and etc.
that's right. So just product of the PDFs.
What is Y?
Mu I is something that I decide. It's a constant,
So but
arbitrarily chosen.
yes.
Yeah. So these are arbitrarily constants. So I get m of t. My first question to you is, do you see that E of m of t is equal to 1? Expected value of m of t is equal to 1.
Looks like it's a argument, this one is not a clear.
There is no Brownian motion here. These are just random variables. Xi are just Gaussian random variables, right?
Condition of the previous discussion.
I see, that's what you mean. Yeah, sure. But I mean, you could also just say homogeneous function. What's expected value of e to power alpha x when x is normal 0, 1? It's equal to,
Yeah, what is left out, what's the condition and everything contains of S is a. You don't need.
they're independent, right?
Oh, we just want to show the expectation is not.
Yeah.
UI xi is 0, and then we get.
So I'm going to just, when I evaluate this quantity right here, I'm just taking expectation of this guy, right? And these are independent variables, so expectation of the product of these independent variables is product of the expectations. Okay. And I have that E of, yes. That's why I've subtracted with just the right quantity.
So go to that e to the 5 minus y, mu y square by 2 minus mu square by 2. With your expectation of mu y xi
Is
just be
mu I square by 2. Yeah, E of mu square by 2. This should not be so confusing, right? I mean, I know. I mean, what you have to also notice for Gaussian setting, whether I have minus mu I or plus mu I, doesn't matter. This will still be e to power mu I square by 2. Okay. So because of this fact, these are independent xi's. I just compute these expectations separately, and I get expectation of 1. So you're with me on this, right? Okay, all right. But the point is now I can come up with a new change of measure with this m of t on this space. So Q of A is the new change of measure, right? Uh, if I define my GIX in the following manner, you can check GIX is actually a probability density function. Can you see that? I mean, you have to again go back and see the fact that f of x is, what is f of x? Huh?
1 by square root 1 by root 2 by.
No integral. ठीक है? So now when I combine this, what do I get? What's GIX?
1 by 2 by
Root 2 pi.
minus x square by 2 minus 2 pi.
Just do it with here.
Start of point.
Yeah, it's just x minus mu I, the whole square. Yeah. So it's a PDF of Gaussian variable with mean mu I.
By
No, with mean mu. Oh yeah, by 2 is here. ठीक है? हाँ. No, I meant here. Yeah. Yeah. Oh, you see my handwriting. Yeah. So you're allowed. Yeah.
Speak about the PDF or random variable that implicitly requires some measure which we're talking about.
Yeah.
So, when you say GI is a PDF of NDYI,
Yeah.
so with respect to the Q measure or with respect to the P measure?
Right. I mean, right now, this is just a algebraic expression here. But when I say that's a PDF, then I'm going to say it's with respect to the Q measure.
Q.
Yeah. And I'll argue why. Because what I've started with is I've defined for you random variables x1 through xn. So that has, and I've said, okay, that has some PDF each. So that under the probability measure, that tells me how to assign distribution to different sets. Okay? Yeah. Now I'll define a Q measure on that same space.
Yeah.
And I need to tell you how to assign probability there, and that'll correspond to PDFs, GIs. There's a no, it's all already normalized, this guy right here, right? This is a proper PDF. Dekho, when if you go back to the expression here, fx1, fx2, fxn into m of t. M of t is right here. It's all normalized, yeah. Okay. So what you get just from calculations, you can see that your Q of A has the following form now. Right? Q of A would be m of t times f of x1, f of x2, f of xt, right? dx1, dxt. M of t will be distributed amongst the different PDFs, and I get g1, x1, gtxt. So under Q of A, the variables x1 through xn, xt, x big T, now are normally distributed with mean mu1, mu2 through mu t. Okay. So that's the same idea we're now applying in a simpler setting. We have this probability space where we have these independent variables. We choose a m of t, which allows us to change a measure, under which now these random variables have a different distribution. So is this kind of clear? Okay. See, this is different from just taking xi under measure p. And so what's happening? The mean is becoming mu I. No, mean is mean is becoming mu I, right?
X minus mu I.
It's minus mu, I think, yeah. Yeah, it's.
Think of X minus mu I, right?
See, think about this. Minus y minus y.
No, if I do the calculation here, you should have corrected me. This would have been e to power minus
Oh,
x plus mu I
X plus mu I, yes.
squared by 1 by 2. So it's the mean has become minus mu I here. So my point is I could have taken xi under p and subtracted mu I from each of the xi's. And that would have been one way to get random variable which has distribution Gaussian with mean minus mu I. Just by kind of, that's all I'm doing right now. I'm reweighing and getting that. Same random variable now has a different distribution, not a different random variable. That part is clear? So this is kind of the important. Yeah. This needs to be.
Such that Q of A is equal to expectation under Q of MT indicator.
Yeah.
So what we're saying is they should integrate the same way.
Actually, it should be. This should be.
Like this, what do you want?
Yeah. No. I guess this should be Q of X in A. Anyway, these are technicalities. You can make.
That's right.
Yeah.
We define that how can you say that Q is equal to that? We define Q GI as this one.
Yeah.
We define GIX as this function.
Mm-hmm.
So now you say that Q of A is equal to that. Think about what is Q of A? It is empty is exactly G1 dot G2 dot. Empty is just E. Okay. Empty is E into some basic. Empty is E to the power something to think I. It to F1 X.
Okay, so what's your point? That's how, if I've now defined for the vector x1 through xt, I've defined how to assign probabilities to them, right? To every set. And that probability corresponds to them having a PDF of Gaussian.
Yes.
So then they have a PDF of Gaussian.
Okay, I scroll back one slide. Let me just read that 1 second.
Yeah.
Yeah, look that. Okay, this makes sense. Yes.
ठीक है.
This makes sense. More makes sense.
So this is, we say that each xi has PDF,
So
and x is a vector here.
what we said for every set,
Hmm.
we've changed what the integral, what it evaluates to.
Yeah.
Right?
Yeah.
The same set.
That's right. Yeah.
Yeah.
That's right. The same set now has a different probability. These are probabilities assigned by new Gaussian density.
Q is equal to Q of A, which
No,
doesn't
no,
make sense.
no, it doesn't make sense. Yeah. Uh-huh.
Something that under a given measure, you will be stuck with, we end up with
Well, it depends on your M of t. I mean, I can choose my M of t to be anything right now. Yeah. But what do I, in some sense, what is this M of t if you see it closely? All I've really done is I've taken my M of t to be equal to f of, okay, hold on. I've taken it to be equal to g of x1, g of xt, f of x1, and I guess there's a 1 here, there's a t here. So now if you wanted your g to be any distribution, even you can have it any arbitrary joint distribution. This need not be a product measure in the numerator, right? Even then everything would work out. Okay? All right. Yeah, so all of this is very nice in the discrete setting. I can go from any measure to any measure. In continuous setting, there are limitations. So yeah, so it's, I mean, what happens is the likelihood ratio blows up very fast. So I can't just put arbitrary joint distributions. I mean, I run into fact that my denominator is assigning zero probabilities to sets which my numerator is assigning positive probability to. So that I cannot do. So when I do this change of measures, my diffusion coefficients don't change. I'll talk about this later. Only the drift I can change. Yeah. Okay, so let's carry on. How are we doing on time? Yeah.
He said that 41 again.
Yeah, no, it's.
What's it 9? Yeah, that's the point.
Yes, I have no idea. When I do at home, it's fine. Yeah.
9:40.
That's why it's particularly confusing because at home I develop a lot of credibility. Okay.
It might be some marketing, like it might be some marketing.
Chalo guys, let's carry on. So we'll do Krasnov's theorem. I guess we'll do it next time. But let's come back to the two security model. Okay, so we have these two securities. So let me just run this ideas by you quickly. So DST is mu t st dt plus sigma t st dbt, and I'm allowing mu t and sigma t now to be more general. They can be adapted processing, need not just be constants. DRT is RT, small rt, big RT dt. Small rt can again be adapted, can be very general. We don't have to keep it limited. Select p tilde t so that dp tilde t given in the following form is Brownian motion. I can do that. I know how to do my change of measure. Take it. Okay. So then I can rewrite my DST here in the following form. So being kind of, I'm using this heuristic notation of DTs, but everything is true, with the integral notation as well. It's just easy to do everything here. You should show this to yourself, huh? This is,
What would be the motivation behind changing the measures here? Like, what will I get out of it?
yeah. So why am I changing measures here? Tell me. I want to show that if I look at the discounted stock price process, there's a alpha T which makes it a martingale. And that's tying up to our whole idea. That we are going to look at ST, we are going to discount it by RT,
Oh, yes, yes.
and we'll come up with a change of measure under which it's going to be a martingale. And then we are going to claim that option price process that we replicate will also be discounted, will be martingales. Yeah, with this measure that we'll identify.
P tilde T was our empty into our original P.
Uh, P tilde, well, once I've given you alpha T, you know what P tilde T is going to be. Your P tilde is going to be. Right? So you can figure out, Grasnoff's theorem will tell you how to find a P tilde so that this guy is a Brownian motion. It'll just be that exponential term with the alphas, the integrals of alphas.
Yeah.
Right? Take a, so this will give me a measure under which now this quantity is going to be martingale. So I have a lot of flexibility now. I can tune alpha T the way I want. That's a big thing, right?
What we write for martingale?
What's that?
We had to show the middle here. You're just showing how distribution can change.
Empty. You mean the Gaussian example? This is just a Gaussian example, huh? Just to kind of tell you that in simpler setting where everything is clear, what's going on. ठीक है, chalo. So the point is, under this change of measure, I have this process looking as follows. I mean, not as a change of measure, but I'm just writing dBT as dP tilde T minus alpha T dt. ठीक है? And if I choose now my alpha T as follows, right? Mu T minus RT upon sigma T, then I get dS is RT ST dt plus sigma T ST dB tilde T. You see that, right? So now I'm claiming that this is having the same rate of growth as risk-free security. Okay. Later I'll show that DRT, I guess DRT inverse by ST, the discounted process, is going to be a stochastic integral. Is this okay? Mu T minus RT by sigma T. So I have mu T minus RT by sigma T dt. So I want to cancel this term here. Okay. Sigma T will cancel with this guy right here. Mu T will go away, RT will come there. Okay. So I get to have a new drift.
That's what I just want to clarify two things.
Mm-hmm.
Firstly, the equalities we're talking about are almost sure equalities, right? So they are implicitly in some measure place.
Yeah.
So this DST equals root PST, is that in the P measure space or in the P tilde? Is it both?
I mean, the underlying space is the same. You have two probability measures which are equivalent on it.
Right. So, but when you talk about like almost sure equality, you mean
Yeah. So they're both
equivalent measures.
they're equivalent measures. Yeah. So in both the measures, this is true.
And this rate of growth we haven't defined formally. What that means.
Yeah, we're not defining it.
So just to understand what you're saying is we have the stock price process.
Mm-hmm.
We can represent it differently with this alpha T into a different target.
Yeah.
Now we can find alpha T such that it grows the same as P.
That's right.
So because in an equivalent measure it's growing at the risk of security, we somehow will bring in that no arbitrage concept.
Yeah, we'll come up with we'll define the option price process.
Right.
We'll come up with a portfolio which matches the option price process. We want to exactly replicate the option prices. Yeah. But now we are, remember how we did discrete finance first we had this option price and we replicated at each and every node. And then we said, okay, this replicating process gives the price of the option. Then we said, let's look at everything under the new change of measure, where all the securities have the same rate of return.
Yes.
Then we discount them, then all the securities are not changing at all. They are martingales, the discounted processes. So any portfolio I construct with them is also a martingale. And then we said any option price process can be replicated by a portfolio. No, by a portfolio. By self-financing portfolio, because my market is complete. So those are issues we have to deal with. But this portfolio that I've constructed now, under this change of measure is again a martingale. So hence the option price process is also a martingale, because it's being exactly replicated by this portfolio. So that's the big conclusion we want to reach, that our option price process under this change of measure is a martingale. So then that, because it's a martingale, it will satisfy some Feynman-Clark conditional expectation equation. So we'll find a PD that it satisfies. And price can be written as an expectation. So all those things we want to come derive in this setting.
Because then equivalent martingale measuring system, we have state prices.
Yeah. So equivalent martingale and state prices are one and the same thing pretty much, right? There's just one is just a normalized version of the other. But to show that the equivalent martingale measure exists, we have to show that under no arbitrage condition we get that, right? And so we needed conditions on the market for that to work. I mean, the point was we should be able to replicate each and every portfolio. So that requires certain mathematical structure. So we'll discuss all that stuff when we get there.
Okay.
Yeah, guys, take attendance. ठीक है, हाँ, go ahead. Yeah.